Okay. Okay, welcome back. So I didn't want to waste your time drawing like all the things like for boost converter. So like I did it already. So this is the boost converter. I did the same thing that we did for the buck converter. For the boost converter, I have all the plots for the voltages and currents here. So we've done this before. I found out last night that I made a mistake when I taught this in ELEX 3130. So I made a mistake in calculating ILDC. It was just like the last few minutes of the class, so I made a mistake. So I'm gonna please pay attention. I think I did it correctly in 4420, but in 3130 I made a mistake in calculating ILDC for boost converter. I told you that like ILDC it's going to be equal to IO, which was the case for buck converter, but you'll see that for boost converter is actually not the case. So let's actually take a look at these plots carefully. So for the time that switch is on the inductor we have V in, and on when the switch is off we have V in minus VO. The diode is conducting. When the when the switch is on, diode is not conducting, right? So we would have 0 here and negative VO here. So the voltage across diode, it's going to be negative VO. That's why it's off. And when it's conducting, it's going to be 0. The opposite for the switch, when it's conducting, this is going to be 0. And when it's open, at this point we have 0, but at this point we have VO. So we have VO across the switch. The current, this one is similar to what you saw for the buck converter, just the slopes are different because the voltages are different. Again, this is similar. This is IDT, right? So this is the current. Like when the diode is not conducting, it's 0. When it's conducting, it has the same value as the IL. The same as the switch. When the switch is on, it has the same current as IL. When it's open, it's 0. For IC is equal to okay, so for this part, for when the switch is on, this diode is off, so IC is basically negative of IO, right? Because we only have an RC circuit that like the same current goes through R and C, but because of the notation direction that we chose for IC and IR, IC is going to be negative IO. You know that this is an RC circuit. Like in practice, it's going to be an exponential thing here. But because we assume that a capacitor is large enough that within this much duty cycle, I doesn't change, we can assume that this is constant. So this is going to be negative IO. When the switch is off, the diode is conducting. We know that IL is equal to IC plus IR. So at this point, IC becomes IL minus IO. So it's like as if we have this line and we shift it down this much. Okay. Now, what does amp second balance or charge balance tells us about this graph? It would tell us that this area has to be equal to 0. I didn't do a good job drawing it. It's like if I want to be more realistic, it has to be something like this. Maybe. Right, so this is this part, this line, which is the half point of this other line. So this is going to be ILDC minus IO. Right, this should be in the half point of it. Okay, so the whole area has to be equal to 0. This area is IO times dt. And this area, which is in the negative part, has to be equal to this area of this trapezoid. But the area of this trapezoid is the same as the area of this rectangle. So I can write it as ILDC minus IO times 1 minus d times t. Okay, t's cancel out, and then I have IO times d is equal to IL dc times, I'm just going to write 1 minus d, minus IO plus IO times d. These would cancel out, and we find out that ILDC is actually IO divided by 1 minus d. Okay? ILDC is equal to IO divided by 1 minus d. Did I make a mistake here? ILDC is equal to IO divided by 1 minus d. Yeah. Okay. Yes. IO times d is equal to ILDC minus IO times 1 minus dt. These cancel out. IO times d is equal to IL times 1 minus d minus IO plus IOD. These cancel out. IO is equal to ILDC times 1 minus d, or ILDC is equal to IO. Yeah, so this is what we have for the boost converter. And I made a mistake that when I taught this in ELEX 3130, I didn't do the calculation. I just told you that ILDC is equal to IO, which is wrong. That's only true for the buck converter. For the boost converter, this is how you can find ILDC. Okay. Let's continue with the calculation. ILAC RMS is the same as how we calculated it for the buck converter. So it's going to be delta IL divided by 2 root 3. Then for I sub D DC, okay, this is going to be 1 minus D times 1 minus t times ILDC, or I can replace this one with IO times 1 minus d. So this actually cancel out. So IDDC is equal to the IO, which is kind of like very obvious here, because I of diode is equal to I of capacitor plus I of R, and the average of this one is 0 amp second balance, right? So the average of ID has to be equal to the average of IO. The same thing for here. This is not going to be 0, but like the same concept. This is going to be D times ILDC, so I can replace it by IO divided by 1 minus D. Okay. Let's calculate the RMS values for I sub D AC RMS. Let me just do the capital. RMS is equal to square root of 1 minus D times ILAC RMS, right? So it's going to be times delta IL divided by 2 root 3. And for this one, IQAC